Okay, good afternoon. I think we can begin today's session whilst we wait for the others to join. Okay, so good afternoon again, participants, students, and stakeholders joining us from Ghana and beyond. You are warmly welcome to the Ghanaian Stakeholders Pre-Conference. So this is organized in preparation for the African International Conference on Quantum Computing and Simulation, which will be organized in February 2026 next year. So without wasting of time, I'll begin today's session with a brief opening prayer. So we can bow down our heads so that I pray. Heavenly Father, we thank you for bringing us together for this important gathering. We ask for your guidance, wisdom, and clarity. As we share ideas and learn from one another, bless our speaker, our participant, and all efforts toward advancing science, education, and development. May this session be fruitful, inspiring, and impactful. Amen. So, once again, I warmly welcome all of you to today's meeting. And we appreciate your time and commitment and in the advancement of science and innovation and in the national development. So my name is Henry Elon-Kwashi, and I'll be your MC for this session today. So today's session brings together policymakers and academics, students, and stakeholders to discuss rapidly evolving area that will shape education, industry, and research for decades to come. I'd like to especially welcome Richie Wellington, if he can give us some few words for us before we start our session for today.
Okay, thank you very much, team, and let me congratulate you once again for yet another round of a preparatory, meeting towards the February conference too. I'm happy to also see Claudia, speaking to us today. Claudia is a key person when it comes to the 2025 International Year of Quantum Science. Yesterday, I was talking to Henry, and I re-echoed the fact that Ghana and Africa has an opportunity that we must not miss, and I believe that we will all bring ourselves together, all the universities in Ghana, public and private, as it lies within our remit to include them. Whatever we're doing to promote quantum science and frontier science must be inclusive. That is what UNESCO is looking for. And I believe that is what sits well with all the plans and the programs that we have been championing in the last 1 year. So with these few words, I can assure you of the Commission's support and guidance, going forward in our conference and also for the legacy project. So I thank you very, very much. I'll stay with you for a while, and I'll have to jump out because I'll be attending the planning committee of the closing ceremony. So I'll be with you for a while. Thank you very much.
Thank you very much also, Richie, for such presentation. So to move forward, our theme for today's pre-conference is the benefits of quantum science and technology across multiple fields and their key impacts on the UN SDGs. So quantum science is driving a new wave of technological progress, as we know, and it spans across all areas in cybersecurity, advanced diagnostics, and then financial optimization. So just to move straight, I also want to introduce the guest speaker for today. It's my honor to introduce our distinguished guest speaker, Claudia Fracchiolla. She is the head of public engagement at the American Physical Society and serves as the Secretariat coordinator for the UNESCO-endorsed International Year of Quantum Science and Technology. She leads the global operations for AoCIQ, working closely with UNESCO, national committees, and international partners to promote inclusive, responsible, and collaborative quantum initiatives across the world. So, without much ado, I would like us to introduce to welcome Claudia for her presentation.
Thank you, and let me go ahead and share my screen. And so, hi everyone. Good day to you all. I first wanted to say thank you for the opportunity to be with you here today, and thank you for that introduction. So, as Henry said, my name is Claudia Fracchiolla, and I am the head of public engagement at the American Physical Society, and that means many broad things, but mainly is that I support scientists to engage with diverse audiences from government officials to kindergartens in school. And then I also serve as the role for Secretariat of AoCIQ. Now, I'm going to talk here today, and before we start, I wanted to be transparent in one specific point. My background is in physics, but I'm not a quantum scientist. Uh, I don't build the computers or design the cutting edge sensors. My job is actually to, as Henry mentioned, help people understand what these technologies are and then build bridges and dialogues that make sure that when the technologies are here, they're benefiting all. Um, and a big part of my path comes from my own personal story. So I started my career in physics back in Venezuela as an undergraduate student, and I was fascinated then by quantum algorithms. But I wanted to do research in that area, and I had reached out to a professor of mine at the university, and he said, unfortunately, you cannot work on that because there's no local expertise, there's no networks that I could plug into to help me develop that research. So I had to then change and do high energy physics, and I study neutrinos instead, so particle physics coming from the sky. And I love that work. But that experience showed me something early on that has shaped what I see. My goal in my career is that access determines participation, and that while talent exists everywhere, opportunity does not. And so this is the lens through what I see quantum today. And this talk is not about quantum as a scientific field, but as an ecosystem, a global network of people, ideas, and opportunities that will take to make that ecosystem serve the Sustainable Development Goals, which is the framework for the International Year of Quantum. But before we started, I wanted to get a sense from you. When you hear the word quantum, what comes to your mind? And I'll just give you a few seconds, but you can either join with the QR code or go to slido.com and use that code to join. And this is to help me set up the way that I speak to you about quantum as moving forward. So I'll give you a few seconds. Interesting. Okay, very good. Great. So before we go into those details that you were talking about and jumping into the technologies, I want to start with something more fundamental. When we hear quantum, we think about all these tech work and futuristic, but nature has been quantum since its existence. Like the sun shines because tiny particles can tunnel through energy barriers and allow nuclear fusion to happen. Or plants use quantum effects to do photosynthesis, moving energy through their leaves, or the structure of matter and atoms and the way their stars are formed. It's all governed by quantum rules. So the story I'm telling today is not about new physics. It's about learning to master the physics that has always been there and apply it to human challenges. Now, I want you to indulge me for a second, because as I said, like I'm a head of public engagement, so that means in big part that I help in ways to communicate the science better. Um, and it also connects to why we're here today. Because the word quantum is everywhere nowadays. It's in science fiction movies like Quantum Mania that was released a couple of years ago, in self-help books, even in commercials. It signals something that is mysterious, powerful, high-tech, is often associated with the word weird, um, and or use as a marketing strategy to signal innovative products that are meant to attract consumers. But in physics, quantum mechanics is the theory that governs how the macroscopic world works. It describes how atoms and subatomic particles behave, and it explains phenomena like the atomic structure, electrical conductivity, how energy is generated. So when we talk about quantum today, we're not referring as something abstract. We're talking about these principles that have shaped our world, and the new possibilities that arise as we learn to harness them more deliberately. And I want to point out a little bit of history because it's relevant to why we're celebrating the International Year of Quantum. Now, we hear constantly now that we are on the second quantum revolution, and that signals that there was a first revolution. And this one began in the early 20th century. So around 1925, a small group of scientists fundamentally changed the understanding of the universe by developing the theory that we use today to describe how atoms behave and light interacts with matter and energy organizes at microscopic scale. Now, to see why that first revolution was so transformative, we need to understand two principles of quantum mechanics so far. The first one is quantization, as somebody mentioned, the word discrete. So certain properties such as energy or momentum exist only in discrete packages, or quanta, which is where the word quantum comes from. So it is like a staircase instead of a ramp. You start on one step at a time, but you cannot be in between step. So these help us understand the internal structure of atoms and how electrons move between energy levels. The second principle is the wave-particle duality, and that is one of the most fundamental concepts in quantum mechanics. What this means is that particles like electrons or photons can exhibit both wave-like and particle-like properties. So in one experiment, it might show that an electron diffracts as a wave, but it becomes localized like a particle when you try to measure it. Now, once those principles were understood, we realized that by manipulating large group of electrons in materials, we could design devices whose behavior follow these quantum rules in predictable ways. So one of the most important examples is the transistors. Transistors work because electrons occupy discrete energy levels in material. So by turning those levels, we can turn electron signals on and off, which are the zeros and ones that are fundamental operation for all modern electronics. And then around the same time, understanding the behavior of light gave us the rise to the laser, which means that these coherent beams of light that today power like global telecommunication, barcode scanners, eye surgery, manufacturing, and other critical things. Now, that was not only the first revolution didn't only impact just telecommunications and electronics. It was also fundamental for medicines. And for example, the quantum property called spin help us develop the magnetic resonance imaging, so MRIs. And these allow us today to see inside the human body non-invasively to detect tumors or see lesions without having to cut a person up. At the same time, quantum chemistry, which means the understanding of how electrons in molecules behave, gave us the way of designing new materials and pharmaceuticals instead of having to rely on trial and error. Now, there's also a revolution on the industry aspect, right? When quantum magnetisms help us understand and develop new materials for power generation, data storage, and electronics. So understanding the energy bands in solids allows to shrink semiconductors from bulky components to nanometer scale circuits so that we can put billions of transistors to feed on a single chip, right? So like this is why we have our tiny phones today have more power computing than those the computers that were used to put a man on the moon. So the first quantum revolution gave us the tool of the digital age. Now, what has changed? In the first revolution, we learned to control flow. So by these, I mean we had billions of electrons or photons moving together inside materials, and it was like guiding a powerful river. We can build dams, channels, and valves to steer those currents. But then today, we're no longer limited to controlling that river. We develop tools to isolate and manipulate a single particle. So a single electron, a single photon of light. And when you can control nature at these level of precisions, the rules of the game change. Now you begin to unlock quantum in behaviors that completely disappear when particles move in large crowds. So these single particle effects are not just scientific curiosities. They help us open doors of new ways of sensing, communicating, computing that were physically impossible before. The shift from controlling billions at once to controlling one is what has marked the beginning of the second quantum revolution. Now, as for the first one, these mean that we need to have a sense of understanding. We don't need to follow the mathematical in depth, but like having a notion of what are these new behaviors that we're able to control, because they form the foundations of modern quantum technologies. The first one is superposition, and the best analogy that we all hear about is that superposition is like if you think about a coin, and when you have the coin, you flip it and turn it down on the table or on your hand, it's either heads or tails, right? So it's like a beat. It's either a 0 or a 1. But in superposition, it's more like the coin is actually spinning, and then while it's spinning, is not head or tails, but it's a combination of both until you finally decided to measure. And then the second principle that we are now able to control is entanglement. And that was one of the words mentioned at the beginning. So this is one of the most counterintuitive phenomena in physics, because if you imagine that you have those two coins, and these coins are mysteriously linked by a cable that we cannot see, and that if you have they're spinning at the same time, and then you catch one on one end, and then it lands on its head, or a 0, for example, then the one on the other side instantly decides that it wants to be tails or a 1. Even this happens even if it is across the planet. So by harnessing these two principles, we aren't just making things a bit faster. We are unlocking entirely new capabilities. So what do we actually do with these principles? When we are able to encode information in these states, and build systems that can store, process, or transmit information, then we are entering what we call the quantum information field. And if we think about it, this is like a new technological alphabet. Instead of bits, there are 0s and 1. We now have states that can exist in combinations and correlations that have no classical equivalent. Now, from this, we have 3 new pillars of quantum technology. The first one is quantum sensing. So in this case, we use quantum states. Like we know that quantum states are extremely sensitive to the environment. So these allow us to measure magnetic fields, gravity, and time with extraordinary precision. Then we have quantum communication. And in this case, we're using quantum effects where we can distribute information in a way that makes eavesdropping physically detectable. And this is not just a mathematical difficulty. I'll talk more about this following up. Then we have quantum computing, which is the one that most people have heard of. And this is like building networks of qubits that can explore, simulate complex problems, especially in chemistry and materials. So as we move into the next slides, we want to get us out of the hype that is what we're talking about, the second revolution in quantum computing, and show you how these pillars are actually standing today and how they're serving global needs now and in the years ahead. But before I do, I wanted to ask real quick, again, another question. Which one do you think will have an impact in society first? And I'll give you a few seconds for this.
Is the communication, madam?
Quantum computing is what most people are thinking, or communication. Yes, brilliant. All right. So let's talk about these examples. So in quantum sensing, as I mentioned, the key idea is that quantum states are very sensitive. So a tiny change in gravity, magnetisms, or temperature leave a measurable signal. In computing, that sensitivity is a challenge, but in sensing, it becomes a superpower. So quantum sensors let us measure the world with precision far beyond what classical instruments can do. And many of these tools are already leaving the lab. So some of these examples are ultra-precise navigation, advanced medical diagnostics, monitoring infrastructure or environment. These areas where quantum technologies are already reshaping how we detect, understand, and manage the physical world. And I'll provide specific examples later. The second is quantum communication. So most of you believe that this is the one that is going to have a bigger impact sooner. So classical communications rely on math for security. So we use very complicated math problems as encryptions that takes a long time for computers to solve. But that is changing. Quantum communications works differently. So it uses quantum state, and if someone tries to intercept a quantum signal, the act of observing is like the act of measuring the state, and the act immediately changes the state. So that the disturbance cannot be hidden. It's not necessarily unhackable, but that you can determine it. So the best known methods for doing this is what is called quantum key distribution, or QKDs for short. And it uses quantum states to share encryption keys that are guaranteed detectability of eavesdropping. And unlike quantum computing, quantum communication is not futuristic. It's already being deployed in national networks and pilot satellite systems. Now we move into quantum computer, and I want to make a clarification on this, is that quantum computers are not just faster laptops. They're fundamentally different kind of machines, so they're designed for specific type of problems. So classical computers use bits, which are zeros and one. Quantum computer uses superposition and entanglement, so use qubits to explore many possibilities at once, because you can have zeros, ones, or a combination of zeros and ones at the same time. And this is why quantum computing is so promising, because it can allow us to simulate very complex problems like molecules, discovering new battery materials, or optimizing energy and logistics systems. But we still are at the very early days. Quantum states are very fragile, as we heard from quantum sensing, and they lose information easily through a challenge known as decoherence. And they're highly sensitive to noise. And because of these, we have very limited numbers of usable qubits, and all these technologies still have high error rates. So building scalable, reliable quantum computers requires major advances in error correction, stability, and manufacturing. There's current multiple hardware approaches to developing a quantum computer. The most known ones are the superconducting qubits, which companies like IBM and Google use. And these ones are the fast and more mature ones, but require extreme cooling, and this is very expensive. The other case are trap ions, which companies like AoCIQ and Quantinuum use. And these are very stable, but they're slower. There's photonic qubits, which companies like Xanadu use. They have the advantage that they can work at room temperature, but they have different control challenges. And then the newest one is the neutral atoms, which are highly scalable architectures, but they're still in their early stages. So there's no single winner yet, but this is normal at this technological state of revolution. And while there is an extraordinary potential for quantum computers, practical large scale is going to take time. And it's crucial to see that quantum computer is just part of a broader quantum ecosystem along sensing and communications, which are already providing real world solutions. So I want to pause for a second to help us ground us back again. Because the iconic quantum chandelier picture that you have on the left, it looks very futuristic, it looks alien, but the lepton on the right is also quantum. Every transistor inside it works thanks to the first quantum revolution and our understanding of electrons are material. I'm pretty sure that when computers first came into the world, people thought of them also at the time as very foreign or alien-like. But what I'm trying to say is that these technologies aren't magic. They're just simply next step on the same story. Quantum technologies are not a departure from the past, but a continuation for learning to control the microscopic world. And because they promise capabilities that classical tools cannot reach, they have sparked a global race that is beyond scientific, is also economic and geopolitical. So in this technological leap, as I said, is not just transforming science, but is reshaping global priorities. And you can see the numbers here. The market for quantum technologies is projected to reach 97 billion by 2035, with sustained growth of 30% each year, and that is huge. The most revealing part, though, is that this is not the future market, the public investment that is happening now. Quantum is now moved from being a niche area of physics to becoming a national strategic priority. And around the world, governments have launched major initiatives, investing tens of billions of dollars into research, infrastructure, workforce development. This has become a global multi-sector movement, which touches defense, telecommunications, health, energy, finance, and manufacturing. But as with any transformative technology, rapid expansions raises questions about access, competition, and global equity. Now, in here, if you see the bar graph that I have on the left, it shows the public investment landscape where you see that China, it's leading with $15 billion invested in developing their quantum strategy. Is followed by the European Union as a whole, and then you have other countries like Japan, the United States, Canada. Now, the map on the right, it's a different way of presenting the data, but it's equally important because it shows a pattern that most funding and infrastructure is concentrated at the global north. And this is telling us two things. First, again, quantum has become a strategic asset for countries that are seeking technological and economic leadership. Countries, nations view quantum as as a critical for not only computing, but security, communications, and advanced materials. The second part is that the benefits and the power currently are unevenly distributed, and the global quantum landscapes risks mirroring or even amplifying existing inequities in the digital axis, such as like research infrastructure and technological capacity. So the question is not just who is investing, but who will have the opportunity to shape the quantum future. Another aspect of that is that, as I said, like there's huge investment in this field. It's very growingly, it's growing very rapidly. But then the gender disparities are even larger than in some other fields. So while there's many jobs being open, only 1 in 54 applications are for women, and women hold basically very little leadership positions in most of these big quantum tech companies. And this isn't just a diversity issue. This is a talent and innovative issue, because a global ecosystem cannot thrive if half the word talent is missing from research, leadership, and decision-making spaces. So in order to achieve a more inclusive quantum workforce is important and essential, not only for equity, but for building technologies that reflect the needs and perspective of the societies that those technologies are aimed to serve. Now, a critical dimension of quantum technologies is what is known as dual use. And what this means is that the technologies, the materials, the knowledge that is created for civilian or commercial purposes can also carry potential for strategic or security implications. So some classic examples of dual use technologies are like carbon fiber. So you can make commercial aircraft or bicycles lighter and more efficient, but it is also used in missile fuselage. Or fertilizers, which are essential for food production, but also serve as precursors of explosive. In the 21st century, dual use has expanded from the physical to also the digital. So what it comes to mind for most people is like AI models that can improve healthcare or help us translate faster, but it can also help generate cyber attacks or create highly realistic deepfakes that spread dis and misinformation. Other things that we also think that are harmless, like social media platforms that we all use, they were initially designed for connecting communities, but that they have become tools for influencing and spreading misinformation and changing political views. So now we are facing the aspect of quantum technologies. They hold extraordinary promise, but they also introduce new vulnerabilities in security and communications, for example, which is why this dual use is not just a physics question, it's a policy and diplomacy question, and one that no country can navigate alone. To move from the abstract to the more concrete, so I want to give a specific example of the dual use challenges of quantum technologies. So one of which is quantum navigation. So we have systems like AQ-nav that has been developed by Sandbox AQ, and it uses ultra-sensitive quantum sensors to read subtle variations in the Earth's magnetic field. So it's using quantum sensing. These allows like ships, aircrafts to determine their position without the use of GPS, even where GPS is unavailable or unreliable. Now, on the civilian side, this is a major safety tool, right? Because it can help commercial aviation, maritime transport, emergency services to navigate, even in the cases where GPS fails due to technical issues, solar storm, or damaged infrastructure. On the military side, though, the consequences are different because this capability allows vehicles to operate in environments where GPS is deliberately jammed or denied. So we have seen these happen in Ukraine, for example. And so this is the core of the dual use, that the same sensor, the same physics can support public safety, but also become a strategic asset. And this is why quantum technologies cannot be governed by engineering alone. So the tools that solve civilian problems can also reshape security, and that's precise where quantum diplomacy begins. And this is not a theory. It is a practical effort that is there to ensure that the technology's benefits are shared broadly and while their risks are managed responsibly. We have seen quantum offer extraordinary opportunities for new medicines, greener materials, food security, climate resilience. But these also introduce challenges that potential impacts on encryption, military use of advanced sensors, concentration of quantum infrastructure in just a few countries. So quantum diplomacy helps negotiate this balance, is shaping norms, partnerships, governance so that scientific progress can support global stability and equity. We support innovation in a responsible way. But it also asks the questions, who defines the rules of access? How do we ensure that the revolution reduces rather than widens the global gaps? How do all regions participate in shaping the quantum future? A responsible quantum future requires an ethical and diplomatic foundation that is strong enough to match the scientific ambition. And because no single nation can answer this question alone, the international community call for a global mandate. And that's where the International Year of Quantum comes from. This was an effort that the final proclamation came on June 7, 2024, when the UN proclaimed 2025 as the International Year of Quantum Science and Technology. And the timing of this was not it was not just casual, right? As I mentioned before, 2025 marks the 100 years since we learned the mathematical understanding and language to observe the quantum world. So now the knowledge driving the technological transformation is what we're also celebrating today. The proclamation recognizes that we have moved from understanding quantum physics to engineering it, and that the shift demands international coordination. Now, I want to also point out that the big achievement is not necessarily that the year was proclaimed, but how these happen. It was a 3-year effort and a bottom-up diplomatic effort to let this proclamation. It started with scientific communities, not with politicians or anything. We did needed a country to bring the proclamation forward. And so in order to work with it, scientific communities reach out to their foreign ministries to show why quantum matters for society. So we had to shift the narrative from the historical mathematical arguments to the relevance to the sustainable development goals. So quantum science is emerging as a tool for health, energy, climate, and food security. So I want you to invite to see International Year not as a celebration, but as a diplomatic mechanism and a global mandate. Part of what that proclamation states is that we need to democratize education, need to build local and scientific technical capacity, and ensure that no country is left behind. So AoCIQ is a shared commitment to ensure that the next century of quantum science becomes a force for just and inclusive sustainable development. Now, the natural question comes is like, who actually drove this mandate? Because as I mentioned, it was not a person or an organization, but countries. And contrary to what many have assumed, AoCIQ was not initiated by traditional technological powers. If you see the countries highlighted in yellow in this map, it shows that 70% of the co-sponsors of the UN proclamation came from the Global South. And I want to take a pause here and offer a moment of very special recognition because while Mexico championed the idea at UNESCO, it was actually Ghana who carried the resolution through the United Nations General Assembly. It was Ghana's leadership, diplomacy, and vision that were central to building broad international coalition that made the year possible. And that contribution cannot be overstated because Ghana helped signal to the world that countries across Africa, Latin America, and beyond are not just watching the quantum era unfold. They want to step forward and be part of the architects of the governance structures, partnerships, and opportunities that will shape this technological future. So why did many countries sign on, including Mexico and Ghana? Because the case for AoCIQ was not just faster computer. It was about the sustainable developments. Countries recognize that quantum science offers new kinds of tools for challenges that directly affect society. And in the diplomatic negotiations, these SDG framing was the decisive linchpin. It showed that quantum is not only a scientific milestone, but a practical contributor to human development. And I know that they still feel very abstract, so I'll provide some more concrete examples of what is happening right now. So the first use case that I want to present is the challenge that the world is facing is that we have bacteria that is becoming faster and faster resistant to existing antibiotics. This is already killing more than 1 million people each year. And traditional drug discovery is too slow and expensive to keep up with the superbugs. So what is happening, there's this project that is looking to speed up the identification of new drug candidates using advantage of quantum computing. So we have molecules that behave according to quantum mechanics. And modeling them accurately requires tracking vast electrons interactions. Classical computers use currently approximations to these interactions. But those approximations start breaking down when the molecules become more complex, which is what we're seeing. So quantum computers, in contrast, can represent these interactions in their natural states because they use qubits, and that follows the same quantum rule. So when I mentioned that quantum computers are not just fasting computers, but they're designed to solve very specific problems, is that they're meant to solve quantum problems, such as this. This is a quantum problem. So the project, it focuses on starting with like classical AI, artificial intelligence, to generate a large number of possible molecules. Then it uses quantum machine learning to learn patterns of what makes the molecule biologically active. And then these can guide the search for new antibiotics by narrowing millions of possible compounds to a smaller set of promising candidates. So it helps filter and prioritize the ones that are viable. And then we use quantum simulation to examine the most promising ones in depth. So it's a hybrid approach, but it can help dramatically reduce the time and the cost of early stage drug discovery. This particular project is a multilateral effort that is supported by the Open Quantum Institute, and it involved the Global Antibiotic Research and Development Partnership, academic and nonprofit partners. We don't have currently fully error corrector quantum computers, as I mentioned before, but we have components of the workflow that I just explained that are already being tested on today's noisy devices and using classical simulators. So to build a foundation for future pipelines. Now, there is a risk, if we go back to the dual use case, if quantum-enabled drug discovery depends on proprietary hardware that is concentrated in only a few companies or countries, and medicine can become inaccessible to big parts of the world. And so this creates a new form of technological dependence. What some of the proposed solutions that AoCIQ is using is that it addresses this by requiring that it is open science. And by that, it means that the algorithms, the models, and the knowledge are shared widely so that the core results maintain a public good status and that any country can build up from there. Now, the second use case that I want to present, it focuses on quantum sensing. And the challenge for society right now is that water scarcity affects billions. There's many regions that depend on underground aquifers for agriculture and drinking water. But to manage these ones is very hard because we cannot see them. So we have traditional methods that use like drilling. This is very expensive and invasive, and it only shows a very small snapshot of the full aquifer systems. We can use technology such as quantum gravimeters that use atoms cooled to a near absolute zero. And these become ultra-sensitive probes of local gravitational fields. So as we said, like quantum states are very sensible. So water in itself is very dense, and changes in groundwater levels slightly shift the local gravity. So while these subtle changes are impossible to measure for classical sensors, these create detectable signals for quantum instruments. So these allow scientists to map and monitor aquifers from the surface without having to drill, and help us track how water reserve can evolve over time. This technology is already being commercialized by European groups called ExAil in France, and they're working together with the National Institute of Hydrology and other teams worldwide. This is already a mature technology and is being deployed already in real-world field campaigns. Now, the challenge is that could create an infrastructure divide because these instruments are very expensive. They require advanced technological expertise, and without intentional cooperation and capacity building, it means that mainly only a few people and countries will have access to map and manage their groundwater. So this is in contrast to how water scarcity is actually hitting hardest in people in the global south. Now, the third and last use case that I'm going to present focuses on quantum communication. And in this case, the challenge is that critical infrastructure such as energy grids, banking system, government data is increasingly vulnerable to cyber attacks. A major concern that is known is called harvest now and decrypt later, which means that hackers are stealing data today that might be decrypted in the future once quantum computers mature. Now, I already mentioned that quantum key distributions can provide a security base on physics because they use quantum states rather than mathematics. And so if an eavesdropper tries to intercept a quantum signal, the act of measuring disturbs the state and it exposes the intrusion immediately. Europe is building one of the largest quantum communications networks called AoCIQ. It involves all 27 UE member states, the European Space Agency, and other industry partners. And this is developing both terrestrial fiber networks and satellite-based links. Now, again, online quantum computer, this is already deployed. Operational QKD networks connect major cities in Europe, China, and pilot satellite links are underway for intercontinental secure communications. Now, the diplomacy risk on this is that without global standards and cooperations, we risk a security divide, where some nations will operate unhackable networks while others remain exposed. But there's bodies like the International Telecommunication Union, ITU, who are working to define open, interoperable standards to equal participation in this process is essential. Now I'm reaching the end and going back to talking about a sustainable quantum future. And what does this mean? It requires an ecosystem that is responsible, inclusive, and equitable. And at the center of that means access and inclusion, because without them, innovation cannot deliver broad societal benefits. Building such an ecosystem means working across 4 connected dimensions. It's education by opening multiple pathways into quantum, so not just PhDs. In society by engaging communities so that the technologies can reflect the local needs and ethical priorities. In industry by fostering innovation that is grounded in responsibility and long-term impact. And then research that is supporting open collaborative science rather than silo knowledge. Quantum diplomacy operates at these intersections, helping bridge infrastructure capacity gaps across the regions. And the message that I'm trying to convey is that quantum responsibility begins with access. So if technology isn't accessible, communities are not included, or the knowledge is not shared, then the ecosystem is not sustainable. My theory of change is that we need to put people and not qubits at the center of the quantum future. And this vision of people-centered quantum ecosystem is not theoretically. We're seeing some of that already happening through the International Year of Quantum. So at first glance, this map just looks like scattered dots, but this is showing a quantum community. We have received more than 1,000 activities and events registered, such as like national summits, workshops, teacher trainings, museums, exhibits, etc. For many governments, these activities are not only outreach, they're early signals of where the national capacity is emerging and where strategic investments might be needed. These also confirm something that we have known, that there is interest in quantum, it's global. But if we look closer to the data, the distribution also shows that there's still work, right? So like Europe currently hosts about 30% of the events, Latin America is 80%, and Africa is at 9%. So it's not that there's no curiosity and interest, but that there might be gaps in infrastructure, networks, and historical access. And that is why events like the conference that you're establishing up in Ghana in February matter so much, because every conversation, every regional initiatives help shift this distribution. Each dot in this map is not just an activity, but a signal of participation. And broadening that participation is at the core of AoCIQ. Now, what are these activities? Nearly half of the activities are centered around education and training, which means that communities around the world don't just want to hear about quantum, they want to learn, build skills, and strengthen their local expertise. There's some research-focused events at lower numbers, and then industry and art festivals also happening. But the biggest thing that we're seeing is that AoCIQ has helped become a mechanism for access, but also that the strongest interest is in building capacity, preparing teachers, students, technicians, and entrepreneurs. Now, who is doing the work? When we look at who's driving these initiatives, about a third of the events come from university and research centers. About 10% are led by nonprofit organizations, and there's some small level of industry and government there. But the key insight is that almost half of the events are multi-sectoral collaboration. So universities are partnering with nonprofits, governments with research teams, companies with other groups. So there's a cross-sector engagement that might not have been possible a few decades ago in the quantum science. And this ecosystem is what we need for a responsible quantum future. Many actors contributing, coordinating, and co-creating. Now, I want to ask one more question before I close, and is what is the most important area that you think for Ghana and the quantum era? And that gives me a few seconds for me to take a water sip. Mhm. Okay. Divided. So I'm not going to spend much time on this because my colleague Heather is going to talk, Dr. Lewandowski is going to talk about that next time. But these infographic that I'm trying to show here, and this is largely based on US data, but it aligns with other trends that we see more globally, is that the quantum workforce is changing. For many decades, quantum has been a niche in physics for PhDs, but today industry in quantum is growing and it's saying something different, that we need people to build things. And technology is moving from the lab to the marketplace, so these requires engineering technicians, programmers, educators, data specialists, etc. People who can turn quantum into practical solutions. And the challenge that we see, at least in the United States, is that education systems still very focused on training researchers. And the fastest growing demand is actually for technical and applied roles. So new jobs are emerging faster than we are able to train people to fill them. So to build an equitable global ecosystem, we need to broaden the pathways into the field and integrating quantum concepts into technical colleges, undergraduate programs, vocational training, and community learning. So democratizing the quantum workforce is not just an education policy, but a development strategy that ensures that countries, including Ghana, can become not only users, but creators and innovators of these emerging technology. And I mentioned a lot about the aspect of quantum diplomacy, and I just wanted to highlight that this is another emerging part of the quantum workforce. We just don't need engineers and technicians and PhDs. We also need people that can translate scientific insights for decision makers, governments, to help represent countries in global forums, to build standards and partnerships, and who can navigate the dual use risk to protect sensitive data or ensure that technology is reduced rather than deepen the inequalities. And these careers some of them already exist, but some of them are being formed, right? So we need to make sure that students also are aware of these paths. Now, to close here, I want to return to where we began. The first quantum revolution gave us the understanding of nature that built today's digital world. The second quantum revolution is about using that understanding to design new medicine, secure infrastructure, finding water, clean energy, and protect our climate. But technology alone is never the solution. A quantum computer can help design a drug, but it cannot decide who receives this drug. Or a quantum sensor can find the water, but it cannot ensure if it is shared fairly. So making these tools truly serve humanity requires something that only people can provide. And I like to say that because people are scared that AI is going to take over. But it's bringing diverse perspective. It's bringing ethical judgment. It's bringing cultural wisdom and helping communities decide together which problem matters. AoCIQ exists not just to celebrate the physics, but to invite you to help shape the next century of quantum science. Whether you are in research, policy, regulation, national security, community engagement, or industry innovation, your perspective is essential. And just by being a bit of poetic here, why 1925 gave us a theory, but 2025 is giving us the opportunity. So what we do with that depends on us here in Ghana or around the world. So thank you for your attention.
Okay. Thank you very much, Claudia, for your insightful and enlightening presentation. So now we'll open the floor for questions and some form of discussions. If anyone has questions, you can just type it or raise your hand, then I'll call you, then you can ask the question.
It was a lot, I know, and I went fast, so I apologize.
Yeah. So I think then I'll go ahead and ask a single question. So with respect to the educational sector, what foundational steps can universities in Africa adopt in order to strengthen their research towards the SDGs in terms of quantum science and technology? Do you have any kind of
So again, I said my colleague Heather will speak more about the development of the education ecosystem for quantum, but I think that the main thing would be a question of what are the priorities for Ghana? And then based on the national priorities, then develop programs that could help support those priorities. So I think that a big part of what I was trying to show in the data is that we need to have programs from the undergraduate level having conversations about quantum. I mean, I'm a big proponent of having quantum even start at the very early on school stages, because when quantum is really going to be huge in the next decades. We live our life in a classical world. We experience it every day and we're conditioned to respond to that. So sometimes trying to understand and work in the quantum space can be a bit frustrated because it shocks with our intuition. And so I always make a case for if we start thinking about quantum from very early stages, then it set us in a different route, building models for things and ways of thinking. So that would be my main take on.
So we wait for some few questions if there's any. So just continue the session and
Hello?
Okay.
I want to ask a question.
Hello. Okay.
Am I audible?
Yes, please.
All right. So that's a very insightful presentation, Claudia. And a lot has been learned. I want to find out, with respect to ethics, is that incorporated in the diplomacy conversation, or ethics is supposed to be a whole new thing to be explored in terms of quantum technology? That's what I would want to know.
So it does follows like all the different elements of a quantum ecosystem, right? Ethics conversation should be on the education, right? When we're training people, we have to talk about the ethics of these technologies with industry partners, right? Like we need to have the conversations about the impact of these technologies and the access to these technologies. And then on the diplomatic side is helping build the policies to ensure that these quantum innovations are ethical. So it is not just for the diplomatics, but it's for everybody in the ecosystem.
So since you highlighted on the diplomacy bit, I wanted to find out if ethics is also being championed in a manner that is deemed to be championed alongside the diplomacy.
Yes, it's a big part. So one of the roles that I pointed out for the in career path for quantum diplomacy is ethics policy officers and regulators who work within can work within like nonprofit organizations or industry, helping determine ethical frameworks for the use and development of these technologies. So it's one of the career paths, but also it needs to be involved in every weave of these quantum technology development. We cannot just have the conversations with the regulators and the diplomats. Like if we start talking about these issues from the education industry and all the stakeholders, that's how we are going to be able to move forward and finding the right policies and building the right tools for these technologies to be accessible and ethical.
Okay, thank you.
Mm-hmm.
I think we have a question from Rabbi Musa.
All right, thank you so much, Madam, for your extensive presentation on quantum science and technology. I think you have delved extensively into the 3 SDG goals, 6, 3, and 9. But I don't know, SDG goal 7, how do you fuse or how do you merge quantum computing to SDG goal 7, which is clean energy? I am thinking that if we are able to have quantum description or quantum application of into clean energy, I think it will go a long way to also address the challenges that we have in clean energy or sustainable energy delivery in our societies. So how do you marry quantum computing to that of clean energy, SDG goal 7? Thank you.
Sure. That's a great question. And so I'm going to provide like 2 examples, but I'm sure that there are others that there exist that I'm not aware of. But as I said, quantum computers are able to help do simulations that were currently very difficult for classical computers. So it can help us find or design new materials for batteries, for example, or for designing more efficient solar panels. So those are 2 ways where the quantum technologies can support the clean energy sustainable development goal. So that model that I show about the OQI with the antibiotics, similar frameworks can be developed for materials for batteries or solar panels, for example.
All right, thank you.
So we wait for additional question then. I think if none, then I'll just move on to the next session. Thank you again, Claudia, for such an insightful presentation. And we thank you also for joining us for this session. And we look forward to hearing from you. Yeah. Okay. So at this point, I would also want to invite Dr. Henry Martin, who is the leader and the coordinator for this program, to give us his presentation.
All right, thank you very much, Henry, and thank you so much, Claudia, for honoring our invitation to speak to the Ghanaian community on the various fields and areas and the benefit we tend to give a quick announcement that as we all know, next week, the same time as 2, just as Claudia mentioned, we'll have AT to come and also give us more insights into how the academia and the industry could be able to relate very well. And just like she emphasized, most of this is within the education and training. And as a Africa that is coming up or gaining the understanding, we need to know how we can relate within different departments, academia. So this is an announcement. The flyer will be going around probably from tonight, but it's just to also announce to everyone that we'll be having Heavy next week the same time. And I think she's even online listening to us to give us moral support for next week. So thank you very much, Henry. That's the announcement I wanted to make.
Okay. Thank you very much, Martin. So we would continue. I think we are almost at the end of today's session. And as we normally do, we take virtual selfies or photographs. So I would kindly request all of us to on our cameras so that we can at least take selfie or photograph for today's session. Okay. Snap. Okay, thank you very much. I think that is it. We had some few of them who left who didn't on their camera, but things okay. So on behalf of the organizing team, we extend our deepest appreciation to our guest speaker, Claudia Fracchiolla, for her time, expertise, and then inspiring contributions. We also thank our coordinator, partners, and institutions, and all stakeholders and all participants for joining today's sessions. So your engagement and support are quite essential. And as we work together, strengthening Ghana's presence in the global quantum ecosystem. So we look forward to your continual participation for our future sessions. And thank you all and have a pleasant evening.